right now we shall begin. And the first lecture for today is Topological Data Analysis for Cosmology, presented to you by Dr. Tymchyshyn. He has got a PhD in theoretical physics and also an education with biochemistry. Right now, he is a researcher at Data Science Center at Kyiv Academic University in Kyiv, Ukraine, where he's doing his research work and also contributing as a lecturer, teaching his own custom in machine learning course. So, Dr. Tymchyshyn, good afternoon to you.
Good afternoon. Thank you everyone for being here. And let me share the
Yes, so
screen.
please, just a couple housekeeping notes before we start. So the lecture is being recorded. I hope that it is okay with you, Dr. Tymchyshyn.
Of course.
Great. So your lecture is going to be for 2 hours as you requested. And as we mentioned before in the invitation letters, all of the questions during lectures will be collected using the Slido platform only in the written form. So if you allow me, I'll just reshare the screen again just to
Yes.
show everyone the QR code. You just use it to follow the links that it provides you. You do not need any registration. You will be greeted with a very intuitive web service that will allow you to write your questions and also upvote questions asked by the others. And there is also one last question for you, Dr. Tymchyshyn. Do you want to have all of the questions being asked in the end of the lecture, or do you want to have a break in the middle so you will answer some questions and some in the end? What will be most suitable for you?
I guess maybe we'll make a break in the middle of the lecture, answer some questions, and then have the second part. So I guess that will be.
Okay, so then please, everyone who is joining Slido using your cell phones, follow the QR code. For all of the other people, I will share the link in our Telegram chat very shortly. So that's all from me. Dr. Tymchyshyn, the stage is yours.
Okay, thank you. So, okay, let me share the screen. And here we go.
Я
I
просто
think
говорю о том, что да.
I guess I'm honored today to be the first one to deliver a lecture in our school, and it so happens that this is, let's say, quite a heavy lecture because it's multidisciplinary lecture, and what we'll be talking about is somewhere in between of physics, of machine learning, like programming, and math. So whatever I'll show you today, that will be, let's say, some sort of interesting mathematical apparatus that you can use to solve a number of different problems, not only in physics, but in many other areas that you may work in or have some interest in. So this is some sort of nice picture for you. There's space and there is some sort of topology. So we'll be talking today about something that has to do with space and with topology. Before I start, just a small thank you to my co-author, Dr. Tsish, because this lecture is, well, based on our work that we have published together, and I want to thank him for his contribution. And of course, I want to thank to Mr. Klevnyuk because he made a contribution into creating this presentation, so his help was really indispensable. Okay, so where are we getting into? First of all, whatever I will tell you today is some, let's say, part of so-called topological data analysis. So maybe you have heard these words like topological data analysis, and maybe you have even seen, I don't know, some practical examples of usage of the topological data analysis. So here are a few slides for you that show different usages of TDA that you may encounter if you work somewhere in machine learning. So for example, here is one of the examples. You may want to use so-called topological features that you extract from data you have. That may be images, that may be some sort of sounds, some, I don't know, time series, so whatever. You can extract some features and you can use that features if you are creating some sort of, for example, neural network. So you are creating some neural network, you are giving an image into that network, it does something, and you want to equip the information that you deliver to the neural network with some additional data on the topology. That may be helpful and that may give some sort of nice results. So maybe you will see that somewhere. Topological analysis of proteins. If you are, let's say, someone into biology and you like all that molecular biological stuff, so you may want to use this mathematical apparatus for analysis of the proteins. So probably you know that the shape of the protein and how all that residues are situated in space they may give you some idea of on what is this protein doing, so what may be its biological role, or some different information on how it works. So probably you may want to use that sort of mathematical apparatus to deal with the proteins. It is even used to analysis of graphs. So I'm not a big expert in this one, but I know that persistent homology is used to detect so-called DNA recombination. As far as I know, they are constructing something that they call arcs. I'm not really sure how do they do that. It's so-called ancestry recombinational graph. Where they trace some sort of genes. And as far as I know, when you see some sort of cycle in that graph, it's like a distinguishing feature of that somewhere DNA recombination was in that species. So maybe you will want to use this apparatus in this case as well. And of course, once again, if you are into biology, I highly recommend you to check this sort of article, and because it's really an interesting topic, not even from some sort of mathematical point of view, but even from a biological point of view. So if you heard about the recombination and I don't know, some terms like holiday structure, they tell you something, for like synthesis dependent strand annealing or something like that. So that may be quite interesting for you, even in terms of molecular biological mechanisms. Once again, about topological analysis of proteins, we can gain some data. We can use these data additionally to give it to some sort of neural network that may analyze the protein for you and gain you some more information on that protein. Anyway, when you are doing some sort of machine learning, you need features. And if these features are nice and relevant, it may make your models much, much better. So, so you might want to check some sort of topological features, and that may be, let's say, good for the results. Get some better results with topological features. Here is some sort of let's say, summary of different methods that you can use. So, I mean, if you have some sort of input data, so what kind of data you may have? So you may have some sort of function. We can get some topological features from the function. You may have a point cloud. So today we'll be talking about point clouds. So I will show you where does it appear and why do we want to work with point cloud in Cosmology. But of course, that point cloud may be something very different that you have from your, I don't know, experiments, some measurements, whatever. You may work with digital images, with matrices, with networks, and so on. And from this input data, you can generate topological features. You do that with the help of simplicial complex. And I will show you today what is this simplicial complex, how do you build it, and what can you do with that simplicial complex to gain some information on what is happening there and what does it have, of course, to do with the topology. So as you see, there are a number of different methods. The one that I use in my works is so-called alpha complex. This complex is close to, let's say, to check complex. They are in some sense equivalent, let's say homology equivalent, and but alpha complex is easier to calculate, so that's basically the reason why do I use it. Because it's a bit quicker to get results when I'm calculating something on the machine. Of course, you may want to use some different versions. Very popular Vitalii-Rips complex. I'll show you an example a bit later. The other ones, I didn't really work with them, but I want you to know that you still have some other complexes that you may want to employ depending on the situation and on the problem that you are solving. So that depends. Then basically we are often generating persistent diagram or barcode. I will show you an example of that. Of course, I am using a library called Vitalii. You see here a number of different libraries that allow you to work with that to get that sort of barcodes or persistent diagrams and so on. I like this one. I like Vitalii. I think it's really nice documented. So even if you know just a little bit about the subject, you can get to the documentation, and you may want to check that documentation and get some idea what is actually calculated and how do you get the result out of there. Ripser, I used it once or twice. It's really quick library, but it's based on Vitalii-Rips complex. But anyway, you may want to use it as well. Regarding the rest one, can't say you much, but at least they exist, and maybe you may want to check what's going on there. And regarding subsequent, let's say, feature selection and so on, we may analyze different aspects of whatever we get out of there. Whatever we calculate, these sort of barcodes and so on, they are tightly connected to so-called BT numbers. So maybe if you know something about topology, you heard about BT numbers. If not, I will tell you today how do we calculate them and what they basically mean, at least at some intuitive level. So that may give you some sort of information about the system under consideration. And maybe you may want to check some sort of distances between the diagrams. So I'll be showing you today so-called Wasserstein distance and some, let's say, limit version of the Wasserstein distance is the bottleneck distance. So I'll show you today that as well. And then you can use this information to, I don't know, to make some conclusions, or you can pass that into some different methods of machine learning, like supervised, unsupervised machine learning, whatever you have. You may pass them to some neural network, or, I don't know, some maybe classical machine learning methods. So whatever you have, you can give this data to that method. And I guess in some cases, you will get some interesting result if you do that. Okay, so there are some different methods from topological data analysis. I'll be not considering them in here, so like dimensionality reduction or something like that. Here is an example from time series analysis. I just want you to know that everything is not just some sort of restricted to the homologies that will be calculated today. There is much more in the field of the topological data analysis. So probably, hopefully, after this lecture, you may want to check some books on the topological data analysis, or at least check what are the topics in that books, and maybe you will find there some sort of tools that will be useful for you and will help you to make your research or whatever you're doing. Okay, so now a little bit closer to the topic that we are considering today. So we are interested, first of all, in using the topological data analysis in cosmology. So what we'll be doing basically, I told you already that topological data analysis is quite a nice tool to analyze some sort of point clouds. So if we have a point cloud, it's a really nice tool that can give us some additional information. Before we dive in, before I explain all the rest, I want to give you some sort of intuitive idea of what is happening and what do we exactly want to get. So, for example, consider for a moment, I have, I don't know, some two volumes of gas. So I have some volume 1 and volume 2. And I want to compare somehow the state of the gas in that volumes. Is that so? I have it in there in one, in second. I know maybe that's some sort of two balloons with gas, and I want to compare its state. And suppose I have whatever information I want about that gas. What should I do? If I consider that as a point cloud, so I may know, let's say, positions and velocities of all the molecules in that balloons. But is it really helpful for comparison? So probably, if you think for a moment, you will think that maybe comparing them molecule to molecule is not a very meaningful operation. So they have all different positions, they have all different velocities, and it's really, you will not expect them to have exactly the same positions or exactly the same velocities and so on. It's unreasonable. So that's not what you do. But what you do, probably if you think for some time, you'll remember that we have a really nice, let's say, branch of physics called thermodynamics. And you say, well, I can calculate some sort of thermodynamical parameters like temperature, like volume, like pressure, so whatever, and I can compare these parameters. And these parameters will give me the idea how close is the state of the gas in one balloon and in second balloon. So here is the main idea. So you have a point cloud. This point cloud is a result of some sort of physical process. I will tell you what exactly is the physical process, but for a moment, just some sort of process. It gives you this point cloud. Maybe you have measured that with some sort of device. Maybe these are some real particles somewhere floating in space. Maybe it's something different. So whatever you have. But it's not very meaningful if you want to compare some two results of experiments. For example, it's two runs and it gives you some positions of some particles or something like that. To do that particle by particle, you want some integral characteristics of whatever you have, and you want to compare that integral characteristics. And it's really nice in the case of gas because we have thermodynamics. We have this really nice, beautiful physical theory, and we can use it. But what happens if you don't have such theory? What happens if these points are results of some measurements or some experiment that doesn't have such a beautiful underlying theory, or is something, I don't know, something brand new, or you have just something modeled on your computer and so on and so forth? What would you do? So basically, you should come up with some idea on how do you get some integral characteristic that is dependent on that, I don't know, positions in space and so on, that will give you some manageable amount of numbers that characterize your system and that you can compare between different systems. So that's our goal. So we have something and we want to perform this sort of comparison. And we need somehow to calculate the integral characteristics to be able to perform comparisons with some manageable amounts of numbers. And of course, we want these numbers to be, let's say, not to feel some small disturbances. So if you do some tiny nudge to one of the points, you don't want your numbers to change somehow drastic. So you want just small changes or no changes, like something like that. So that's what you want. Okay, so now what we are dealing with. So we are dealing with cosmology. So our universe, as you might know, it's not, let's say, at some scales, it's not uniform. But it exhibits some large-scale structures of galactic filaments that form along and follow, let's say, web-like strings of dark matter. And for decades, astronomers have been mapping this network. It's now referred as a cosmic web. and it by different methods. So first they were using some sort of baryonic matter distribution. So you may want to check large optical surveys like Sloan Digital Sky Survey or 2-micron All Sky Survey or or VMOS and so on and so forth. Then they use some sort of diffuse gas signatures in different spectra like X-ray, microwaves, radio spectrum. So whatever they can, they measure everything. But all in all, what do we have? So we see some sort of, let's say, clumps of matter. It's not only baryonic matter, but there is much more, let's say, dark matter in that clumps. And we may consider them as the points in 3D. So we know that we have some sort of physical process, some process of the development of our universe. So starting with the newly born universe from a quantum fluctuation and up to this day. And we know that their distribution, of course, physical laws that we have, they basically direct how matter will be distributed in space. And we want to gain some information from that distribution. So we have all that surveys. We have we can abstract to think about it like we are having some 3D map with a large point cloud, and we want to gain some information from this point cloud on the physics of our universe. Of course, you can't expect for some method just to look on some points and tell you, well, these points were generated with that physical processes or some different. That would be too good. Would be really nice, but we don't have that sort of technology. Okay, so what do we have? We have the ability to model our universe. So what we basically do is some sort of, let's say, educated guess. So we have some model of the universe. What we are using is so-called lambda CDA. I'll tell you a few words about it just in a minute. So what is that and why do we love this model? But anyway, we have some sort of model. And this model, it has some parameters that we are trying, let's say, to guesstimate. What can we do? We can create a computer model that takes this lambda CDM, that performs some sort of modeling, and that gives us some sort of distribution of matter that we should expect at our time. And here we come to the problem of two balloons with gas. So we have the real universe that we observe, and it's one balloon with gas, some volume with particles. And here is the second balloon with gas. So we have some model that predicts distribution of the matter. Of course, we won't expect that the predicted distribution will perfectly match in the coordinates with whatever we see. On the other hand, we should expect that some sort of inherent features of this distribution, they should be connected to the physics behind it, because physics is the thing that generated the distribution. And probably if we somehow can compare them with a different, more, let's say, more smart way than just comparing particle to particle, we may have idea how much did we, let's say, not guess the right parameters or the right model or something like that. So we need some comparison device that will take some real distribution, that will take whatever we have modeled and will tell us, well, they are pretty similar, or, well, they are absolutely dissimilar. So it's not what you search for. So that's what we basically want. So we want this sort of apparatus. And we were trying to use topological data analysis. Well, not only we, there are different groups in the world that are trying to employ topological data analysis to cosmology. Probably the most well-known is the group of De Weygart. Hopefully I'm telling his name properly. So what we are trying to do, we are trying to get some sort of topological information from that distribution, and we hope that this topological information will, let's say, remove some sort of noise or some sort of random component, because it's always present, some sort of random component in whatever we have, and it will retain more information about physics than about anything else, about some random stuff. So that's what we want. So we hope that comparing these parameters will give us something more or less meaningful. Okay, now about the model itself. So just a few words. Here is the slide about distance measurement. So as I told you, we want to map whatever we see, and we want to create some sort of map with the distribution of the matter in space. The model that we are trying to fit in, it's called lambda CDM. It's not, let's say, it's not a model, it's rather a family of models that we have for today. It contains something like 11 parameters, but there are, let's say, different versions of lambda CDA. The simplest contain, I guess, something like 6 parameters. And what we want, and the problem of one of the problems in modern cosmology, is to guess these parameters as good as we can. This is a really nice model because no other model, as far as I know at least, can explain all the observable effects. And the interesting part, if you see its name, lambda, it stays for dark energy. I'll show you just in a moment why it's lambda. And CDM stays for cold dark matter. So this model includes our ideas on the existence of dark matter, and even that this should be some particular type of dark matter, because probably you have heard that previously, when the dark matter was just discovered, there were different theories. So there were theories of warm dark matter and so on and so forth. Now we are getting into cold dark matter. It seems the best choice that we have as for today. And of course, the destiny of our universe, it depends on the parameters. So if you are really concerned with our destiny in the following few billions of years, so probably these parameters will be an interest for you. Well, if not, okay. Okay, what else? About lambda CDM, just a few words, because we are in the realm of cosmology. So why this model? Why is it so good that we all use this lambda CDM? So as you see from the name, it's really crucial for this model to have so-called dark matter and dark energy. So what do we know about these stuff? So we haven't observed directly any of those. But we have some sort of physical measurements and some experiments that tell us that something like dark matter and dark energy should exist. And they are, let's say, the best candidates because they can explain all the observable phenomena that we have for today, and no other theory can do that. I would tell that is a little bit, I don't know, some sort of philosophical thing. So how do we do science, and is it good or is it not? But I was always thinking that it's really good if you have a number of observations and you have some sort of theory that explains them all without any need to change there something drastically and so on. It's a really good sign that probably you are going the right way. Because if you have something that is, I don't know, tailored from few different theories, and you are saying that this one works here and there it doesn't work, there works something else, and so on and so forth, it looks like some sort of patchwork. So it may be a sign that you are doing something wrong, that maybe there is some better explanation and you are just trying to patchwork whatever you have at the moment. And what's really nice about Lambda CDM that it explains whatever we have at the moment, and you don't need any sort of patchwork and styling. It works here, but no, there it doesn't. So it's a really good model in that sense. So why do we know, why do we think that dark matter exists? Well, I will refrain from the word know until we detect that somewhere, but why do we think? So first of all, we know that galaxies in clusters are moving too fast. Stars at the edges of galaxies are moving too fast. So I think I have some sort of slides here. I'll show you that in a moment, or we will return to this one a bit later. Okay, so here is how do we measure all that stuff and how do we gain that information. So here is the hydrogen atom. So as far as you know, it has a proton and an electron. And here you see, let's say, schematically depicted spins of the proton and electron. And these spins, they may be aligned or they may be directed in opposite direction. Let's say so, hand waving. And if you do the math with all that sort of Schrödinger equation and so on and so forth, you will see that the energy between these two states is a little bit different. And if it's so, you can expect that this spin flip will generate you a photon. Or an atom can, of course, take a photon and go from one state to the other state. So this is the quantum state change between the two hyperfine levels of the hydrogen 1s ground state. And it produces the electromagnetic radiation. This is seen as a line of some very certain frequency, and its wavelength is equivalent to something about 21 centimeter. It's not exactly 21 centimeter as you see in this slide. There are many numbers after the point, but you get the idea. So something in that area is that's hydrogen. And if you suppose that hydrogen is everywhere the same in the space, once again, we can't check that. We can't get out even from our solar system. But probably it's really reasonable idea that physics is the same everywhere in the universe, so wherever we are. And using this reasonable idea, you can expect that seeing this line somewhere tells you there is a hydrogen. And what's good with this line, if there is some sort of, I don't know, some gas moving or whatever you have, so these atoms are moving for whatever reason they are moving, you can observe so-called Doppler effect. And if you know the exact wavelengths that you expect, and you see that something happened and this wavelength is a little bit different, it's a bit bigger or a bit smaller, you can calculate the velocity of these atoms, how are they moving. And with the help of the Doppler effect, you can check if you have some sort of galaxy, for example, some spiral galaxy, and you look at the stars at the, let's say, at the border of the disk, and these at the edges of the galaxy, and you will calculate the velocity that they are moving with. And the problem comes here. So in statistical mechanics, you have so-called virial theorem that provides you some sort of general equation that relates average over time of the kinetic energy and of a stable system of discrete particles and potential energy. And if you use that virial theorem, you will see that something is wrong. Why something is wrong? If you calculate the mass just basing on the matter that you see of whatever is glowing, you will see that it doesn't work somehow. So you should have a very different picture. So here is the one, the expected from the visible disk. So here is the picture that you should have, and this is what you are measuring. Of course, at this point, you are free to build very different theories, and people tried, even they were trying to modify gravitational theory and different other things they tried. But the best one, as for today, it seems that virial theorem works and gravity works and everything works, but just the mass that we estimate is wrong. It's wrong, it's too small. So there is something that we don't see. That's why it's dark, because it doesn't glow, we don't see it, but it has some mass. And if you do that, everything is explained perfectly. So that's why it's dark matter. You don't see it, it just doesn't glow. But that's what we have. The other thing that you can gain, once again from the 21 centimeter line of the hydrogen, is the spectrum broadening. So you have a spectrum, and if all these atoms are moving somewhere randomly, once again, you have a Doppler effect. But in this case, some of them are moving towards you, some of them are moving from you, and all in all, everything summarizes in some sort of thermal line broadening. So if you have these sort of emission lines, the spectrum, they will broaden. You can measure that, and you can gain some information on the on the velocities in the gas. And how do we call that velocities in the gas? Of course, it's temperature. So now we may have some idea about the temperature in the gas. And we can measure that in different places in space. And from that, we can gain some more and more information. So we see that there is some sort of interstellar hot gas. And the thing is that if you calculate that without some additional mass that we don't see, that doesn't glow, you won't have that parameters and that temperature that we are observing. I'm not a very big, let's say, expert in that, how exactly that is calculated, but what I definitely know that you have the ability, if you know how much gas do you have there, so on and so forth, you can calculate its temperature expected. You can measure that with the broadening of the lines with that spectrum of hydrogen. You can compare that, and you will see that something is wrong. But if you tune that parameter of available mass that is there with the gas, you will see that your results will be much better aligning with with whatever you calculate. So you really need some additional mass in there. One more effect that you can observe is so-called gravitational lensing. As you know from the general theory of relativity, the light can be bent by just the bare presence of mass. Because if you have some mass present, it will, let's say, deform your time space. And due to this deformation, it will lead to the fact that light will bend. And that's why if you are looking at something very, very distant, here is some distant galaxy, and there is something very, very heavy on the path of that light, you may see that light can bend, let's say, from the right, from the left, and you will get some sort of different images of one and the same thing. So looking at the sky and searching for such sort of anomalies, you can gain some information that, wow, here is something landing. So there must be some mass in between us and that distant thing. And if nothing is glowing there, it should be something dark. So probably some dark matter with some mass is doing all that things. So here is an image. I'm not sure where did I take it from, but here is an example of landing. So probably looking at this image, you will see that it doesn't look quite natural. So something strange in this image. So that's because you see here an effect of landing. So that's what we have. One more image with landing. So once again, and okay. Now I'll return for a moment to this slide. That was about dark matter. We still have some more information that comes from so-called acoustic peaks in cosmic microwave background, and it makes a difference if you calculate time for a large structure formation and so on. So we have a number of evidences that there is something that should have mass, but we don't see it because it doesn't glow. So at least it's the best theory that we have for today. And one more additional thing that we use in lambda CDM is that lambda, that's part for dark energy. And why do we think that we have that sort of dark energy? Well, for dark energy, the number of arguments, it's really much more scarce than for dark matter. But whatever, the first thing, it's an inherent part of the Einstein's theory of gravity. So if you see this this sort of Einstein's equation, you see this lambda there. There was a really interesting story about Einstein who first didn't want this lambda. Then he saw that the universe that his theory was predicting wasn't stable, and he told, well, we should add this lambda. Then he told that adding lambda was his biggest mistake, and so on and so forth. So he was swinging here and there. But all in all, as for today, we think that lambda is crucial. It's much better with lambda. We can predict whatever we see than without it. So it's inherent part of that theory. We can try to detect. So what does the dark energy do? It accelerates the expansion of the universe. So there may be many debates of what is it exactly on the physical level, but whatever it is, the main effect is the acceleration of the expansion of the universe, and we can detect that with so-called standard candles. We can detect that with baryon acoustic oscillations, and it affects some CMB properties and much more. We can even see some sort of effect, so-called Sachs-Wolfe effect. So here is a very famous picture of the cosmic microwave background that you see here. It's analyzed with all sorts of techniques that we have. This is the light that came to us from the so-called last scattering event. So before that, we had light and matter in some sort of equilibrium, and everything, whenever you had a photon, it was at that point, let's say, it disappeared and then reappeared once again, and so on and so forth. And only the event when you have a neutral hydrogen that has no charge, when it was formed, you have the less scattering, and our universe becomes, let's say, transparent for the light. And this is the light that we see at the moment. We are analyzing that. Here is an example of baryonic acoustic oscillations. It's a bit, let's say, a complicated effect, so I restrain from, let's say, explaining that. And I'll maybe tell you a few words about so-called Sachs-Wolfe effect. It's named about Sachs and Wolfe and its property of the cosmic microwave background radiation. So what is happening? If you have a photon and it's going from some, I don't know, very, very far distance, it's going to you. So at some point you will observe this photon. And there is some sort of potential well in the path of this photon. So it may be some sort of mass in between us and the photon, so whatever it is. So maybe some clump of dark matter, so why not? And the thing is that if some sort of, you can think about that, I don't know, some ball that is going down the hill, if it goes down the hill, it gains some sort of kinetic energy. So the very similar thing happens to the photon. When it gets to that well, it gains some sort of energy, and it's, like, let's say its wavelength, it's shifting towards the blue light. So something like that is happening. And now the interesting part. If we just had this well, if you go down, then you go up, you are going up with the same energy that you had when you were going down. So you gain something when you get down in here, But when you are getting up, you are spending the same energy that you have gained when you were going down. So that's very simple, just energy conservation law. But what happens if your universe is expanding? You are getting down that potential well, you are gaining some energy, but when you are down here, the universe has expanded, and when you are going up, this potential well is a little bit more shallow. So you gained some energy going down, but when going up, you don't need to spend it all, because that sort of universe expansion, it did some work for you. It made this potential well a little bit more shallow. And you can basically detect this effect and get some, let's say, idea on how our universe is expanding and so on and so forth. So once again, I can't get very deeply into details because I'm on my own, not a very big expert in all that things, but let's say hand-wavingly, it's something like that. So we have some sort of evidences that our universe is expanding with acceleration, and that's really nicely predicted if you add that lambda constant into the gravity equations, and you claim that we have something called dark energy, so whatever it is, but it's making our universe to expand with some sort of acceleration. Okay, so now to whatever I will show you in the second part. So with this part, I guess we have gained all the necessary intuition about the physical part of all these processes and what we'll be trying to do. So here is some sort of nice pictures for you. That's a result of modeling of our universe. You see all these dots, they are showing, let's say, distribution of matter in space. So we find some sort of, let's say, clumps of matter large enough. We call them halos. So we model the distribution of the matter in space. We find halos, and these halos, they will serve for us as the points in the point cloud that we will analyze. So making such sort of experiments, we can get a number of different point clouds, and then we are trying to do something with them. So we have, at the moment, we are working on two things. So this is, I will share, I guess, this presentation link to it somewhere, and you will find here links to the archive. Here is the first work, it's already published. We have worked with just models, with these sort of models, and we were trying to compare them and to get the idea whether our topological data analysis methods, how do they feel the physical parameters of the system. So if they can somehow feel better parameters of the system, physical parameters of the system than some random things, because of course, if we model, we start with some sort of random seed, so we randomly distribute this matter, we do something else. And of course, we wanted to get physical information, not some random garbage out of there. So we were comparing these sort of simulations and checking what happens in there. The second one is right now under review. So there's more about Betty curves, and can we use them to detect something similar? But let's see how that goes and what I will have time to show you. Okay, I guess right now I'm done with the physical part, and I'm ready to get into the mathematical part. So just a small question. So do we make some sort of small break, or we are just diving in and getting with all that math?
Up to you. We can like read the questions.
All right. So this might be a great stop to answer some questions, I guess, right?
Yes, I
Because we
guess
already
it will
have
work.
a few. So let me just share the screen. This will stop you from sharing, but now I will open my screen. So
Yes,
right now everyone should see menu of Slido from our admin perspective. So we do have two questions. I'll read them aloud, and then Dr. Tymchyshyn, please answer them. So the first one is, why specifically topological and not some other metrics, like averaging, other statistics metrics, are used to create a short description of the system?
Okay, thank you. Well, the truth is that everything is used. So yes, if you check for different works, you will see that people are using basically whatever they can. Of course, if you are doing some sort of, well, let's put it this way. So yes, we want some sort of description of the system with a small number of numbers. So no pun intended. But if this number of numbers is too small, it's really hard to gain some information out of there. So if you do just averaging, yes, you get some really interesting info and you can do something with that. But maybe in some cases, if you want to compare simulations, you may want to get something more. As some sort of analogy, let's think about comparing two pictures. If you have two pictures and you want to compare them, you probably wouldn't like to do that pixel by pixel, but of course you wouldn't like to do that just comparing the mean values of the pixels in each of the picture. So you can gain some information from there, but it's not enough. So basically the answer is that everything is used, but we still want something more because we want some more reliable features that will help us distinguish different models. So we will be performing probably more and more experiments and try something more and more.
Great, thank you very much. And the next question is, from your experience, how much knowledge of topology is needed to get started with TDA, understand papers and books, etc.?
That depends on what you do. To understand that a little bit deeper, you will need some decent amount of mathematical apparatus. I guess in the second part of this lecture, we will dive into that mathematical apparatus. I'll try to explain whatever I can, let's say more or less hand-wavingly, but probably that will give you more or less the understanding of what you are dealing with, to understand that a little bit more deeper of what you do. To use that just as some sort of feature, just to try that, it's probably enough to know some sort of Python because everything is collected into the libraries, so you can pass data in there and you can get data out of there. But of course, in this case, you will probably need someone as the co-author who will be more deeply understanding the underlying mathematical apparatus to help you, let's say, to understand what are you getting out of there and so on. So for start, if you know someone who's doing that topological data analysis, you can help them just knowing almost nothing, just some sort of Python and writing some code in Python. But if you want to do something deeper, you will need some decent amount of topology. Maybe at least some sort of, I don't know, read at least some book on topology and then something about either topological data analysis or algebraic topology. So that depends.
Okay, thank you very much for the answer. So from your answer, I get that it can be possible to cooperate for two people. One of them is a theoretical mathematician who have studied the underlying mathematics that is needed for this subject. And another one is more of a computer scientist who knows programming and also has some mathematical background to kind of understand to some extent what he is doing and implementing, and will be able to understand what his colleague from theoretical math is trying to achieve in his work. So such cooperation is possible, yeah?
Yes, absolutely.
Great.
it.
So this can be like this turning point for many people who are thinking about switching degrees or careers. So that can be for some theoretical mathematician an excuse to dive deeper into the computer science stuff, and also for a computer scientist who is eager to begin his journey in mathematics to do likewise. So great.
Yes.
Okay,
Yes.
so I guess we are out of questions for now.
So let's get started with the sort of mathematical apparatus. Um, oh, great. So right now we have considered all the physics I wanted to consider that is behind all these things, and we have some sort of clear idea. So why are we going to do what we are going to do? And now I want to show you the mathematical apparatus behind this. It's really, let's say, there are some complicated parts. I will try to simplify everything I can to make this as much accessible as is possible. But anyway, let's get into it. So first of all, so once again, many problems in theoretical physics, in many other areas that we have, they boil down into comparing some sort of point clouds. So there may be some physical objects like stars, galaxies, gas molecules. It can be something quite abstract. You can work um, with some sort of abstract spaces, so it doesn't matter, but many problems, they boil down to something like this. And now we are considering this problem, and we are trying to find some sort of nice solution. And the pathway that we will go through, that I will show you, looks something like in this diagram. So we are starting with 2 point clouds, so point cloud 1 and point cloud 2. I will show you some sort of topologically algebraic magic that will transform that into numbers. And these numbers, that will be basically Betti numbers. But if you know something about topology, you know that Betti numbers, they characterize some sort of manifold. So of course, I'm obliged to tell you what kind of manifold are we working with and what is exactly happening, and define somehow these Betti numbers. And then we will get through a comparison procedure, and this comparison procedure will lead us to some sort of result, and will tell us how similar or dissimilar are these 2 point clouds. So that's the way that we are going to get through. I think I may change, I don't know, some ordering of all the things of what we do. So let's get exactly to the simplicial complexes. Here everything starts getting more or less interesting, or no, let's do this part. Okay. Okay, where is it? Let me start some parts of the code. So what are we trying to do now? A point cloud is just a merely collection of points, so nothing interesting in there. What we really need is to create some sort of special mathematical object. It's called a simplicial complex, and we will operate on that simplicial complex and do all the different stuff with that simplicial complex. Why is it so special? This object lives somewhere in between the topology and the algebra. I will show you a few theorems that will, let's say, more rigorously explain to you what it means. But first, let's try gaining some sort of intuition of what we'll be dealing with. Whatever I'll show you right now, that will be a construction of so-called check complex. So there are different complexes. I told you at the beginning of the lecture, like Vittori-Reeves complex, so on and so forth. I'm starting with the simplest one and the closest one probably to the real physical world. So let me create some sort of point cloud. I'm just putting some points in here, and it's merely a point cloud. What I do next, around each point in this point cloud, around each of the points, I am taking some sort of ball. So I'm taking a number of balls, and the union of these balls, that will be the manifold I'm interested in. So that's the manifold whose topology I will be studying. You see that depending on the radii that I endow these balls, I may get different manifolds. So you see that everything in green, that's the manifold we'll be working with. What else? What else interesting is happening in here? Each of these balls, it has equal radius. So all the radii are the same, and this is the number, so r equals 0.15. That's the radii for all of them. That's okay, that's simple. You can do that in space of any dimension. So if you have some r to the 10 even, or to the 100, you can do that perfectly. Create some balls and look at that. Okay, what else do we have here? So you see these sort of edges and these sort of triangles that are appearing when I am changing the radius. So what is happening in here is the construction of the check complex. So probably before I show you how it is constructed, I should tell you what is that sort of complex. There are different complexes, CV complexes, delta complexes, simplicial complexes, and so on. They differ with some sort of restraints that we are putting on them. That's all okay. We are working with simplicial complexes. That's good. But what I want to explain you now for a moment, the complex is simplicial. So it's built from something that is called a simplex. So we have many simplices, and we build a complex from them. Here is an example of simplices for you to just give you some sort of intuitive idea what it is. So this is the order 0 simplex. It's just a bare point. Here is a segment. It's a simplex of, it's a one-dimensional simplex. A two-dimensional simplex looks like a triangle. Or you can have this sort of pyramid, or with 4 different points. And this is a simplex in 3-dimensional space. And probably you can think that you can add more dimensions to this space, and you can create a simplex for each of the spaces by just adding some more and more points to that. So here is some sort of end-waving example. Of course, you can define that more or less rigorously. So if you tell that I'm working with the space Rn, and I take in this space, let's say n plus 1 independent points, the points are independent formally if you take one of them and you calculate vectors to all the rest, because you know that you can take differences between points and you get some sort of vectors, and these vectors are linearly independent, then these points are independent as well. What it means in a hand-waving point of view, if you have a pyramid, it's a pyramid. It's not squished into the plane, because you can take one of the points and put it into the plane to the 3 others, but that will be not a pyramid anymore. That will be not a simplex anymore. So you have squished that. So it's in a hand-waving point of view, it's just don't squish the things. If you have 4 points, they should not be lying on some sort of one line or in one plane. So you don't want that. Formally, you are taking all the differences and you check that the vectors, they are linearly independent. So taking all these simplices, making a collection of them, you can create so-called simplicial complex. The thing is that creating a simplicial complex, it's not just merely taking all the simplices into one big bunch. You should, let's say, restrain yourself with some sort of rules. So not very difficult rules, but just few of them. So first of all, if you are creating that sort of complex, a geometrical complex, so every face of the simplex in that complex, it should be included into the complex. So that means if you are treating a simplicial complex as a list, simplices, I have simplex ABC, I have simplex so on and so on, you should include all their faces and say that they are included into the simplicial complex. So probably I will show you an example right now, so some simple example. Okay, I need to run a part of code in here and a part of code in here, but let's do that very, very simple. Let's take a triangle. So let me draw that on the board. So it's a really simple idea, just to make you not confused with all of that. So let me take, if I want to take a triangle ABC into a simplicial complex, I tell that it's included. So when I'm writing my simplicial complex, let's call it just SC, I should, of course, I take this sort of triangle. Yeah, so I take the triangle ABC. Okay, I guess I use the wrong order. Yeah, vertices. So B is up, C is down. That's a bit less confusing. But together with each simplex, my simplicial complex should contain all its faces. So it has a face AB. It means that I should include AB in here. It has a face AC. I include AC. It has a face BC. I include that as well. Is it enough? Well, not very. This is a simplex as well. If a simplex is included into simplicial complex, its faces should be as well. Does it have faces? Yeah, it does. Point A and point B. So point A, point B, and if I consider the rest, point C, will be included as well. So it's not like a very big deal, but whenever you are trying to write down some simplicial complex, you should remember you have something in there, faces should be in there as well. And that's what you see if we consider this sort of example. So I'll be showing you some examples. And of course, I am too lazy to write down the whole complex that we are working with. So I'll be just writing down the triangles. We'll be working in 2D space. It's to make, let's say, easier for you to understand what's going on. And here is the whole complex. So here are all the faces, points, and so on and so forth. So this is it. Okay. So one more thing, if you have some sort of intersection in the geometric complex, this sort of picture is invalid. Because if you have an intersection between two simplices, that should be their common face. So you can't have something like this. It's not right. If you have two sort of pyramids, you should glue them together using their faces to glue them. So you can't do that some different way. I don't know, some glue half of the face or do something like that. It's not legit. So you don't do this sort of pictures, but you do something like this. So here is the simplicial complex. Okay, why am I so concerned with these simplicial complexes? So first of all, of course, I'll return back to the first demo and show you how do we create that. But the thing is that simplicial complex can be defined in two different realms. It can be defined in the realm of the geometry as a geometrical simplicial complex, with all these points, and you can write down in the 3D space, if I have defined where are all the points of the pyramid lying, you can write down all the rest points as with some sort of very simple formula. I'm not sure. Do I have it here? No, I don't. Okay, let me write it down on the blackboard. So if you have a simplicial complex that has some points, let's number them, it's easier. A0, A1, A2, let's be two-dimensional. It means that everything inside, the inside of it, can be easily defined as all the points of the form lambda I, AI, sum with I, with some sort of restrictions on this lambda. So you want your, why am I writing K, lambda I to be greater or equal than 0, and you want the sum of lambda I to be equal to 1. So these are sort of restrictions on lambda. And here is basically the definition of all the points inside the triangle. Of course, you can think about this formula in a many-dimensional space, so nothing bad happens. Here I take 3 points to work in 2-dimensional space. You can take 101 point and work in 100-dimensional space. So that's perfectly okay. But this is a geometrical definition. Of course, in this definition, you can define faces of the simplex. So faces, it's the case when sum of your lambda i's is equal to 0. So if my lambda I that corresponds to A2 is equal to 0, whatever I get are the points on this line. So I'm moving just along this line. So basically, that's the face. If I am taking, for example, 2 lambdas equal 0, I get this point, and so on and so forth. So the face, if you define it that way, it can be the whole simplex, it can be empty, and you say that the face is proper if it's not empty and not the whole simplex, but that's all mathematical mumbo jumbo. But the main idea is that you can define it geometrically. On the other hand, you can define it algebraically. You can define that algebraically, and you can tell that I have some abstract elements. I'm collecting them. I'm doing some set of some, I don't know, some collection of sets of elements, and I'm saying that it is just, let's say, closed with respect to the operation of taking a subset. So it's something very similar to what I did right there when I was writing down what do I have in a simplicial complex. So I wrote down I have a triangle, so on and so forth. If I forget completely about the coordinates of that points, I'll just, I don't know, just use some sort of signs as I did. I will have some sort of algebraic definition of a simplicial complex. And here comes the magic. So I have a geometric definition, all that coordinates in Rn and so on and so forth. I have an algebraic definition. When I forget about all that coordinates, I'm working with something quite abstract. Of course, I can move from geometry to abstraction. I'm just looking what points am I using right there. I'm giving them some names, A0, A1, A2, and so on, or as I did ABC, as I did for the triangle, and I get my abstract simplex. But it turns out there is a theorem that tells you that you can always find for any abstract simplex a realization in the geometry. So whatever I came up with, any abstract thing, I can draw a simplicial complex in some enough dimensional space. I guess it's 2n plus 1 or something like that. Doesn't really matter, but I can do that. But moreover, it's not over. It's not the whole magic. The whole magic is the following. If you have two realization of some abstract simplicial complex, they are equivalent in a sense that you can find some simplicial homeomorphism between them. So you can deform basically one into another. Thus, they have the same topological properties. And that's really crucial. Why? It means that when you are dealing with the abstract simplicial complex, you are basically retaining all the topological information that you had in geometry. If that wasn't the case, you should have been able to create two different complexes with two different topologies from the same thing, from the same abstract thing. But it never happens. You have the theorem that forbids that sort of thing. And this is the crucial moment. So you can do something in geometry, somehow create all the things, then you just abstract them. And it turns out that that abstraction contains all the information that you had previously. And that's really crucial because now you can work with that abstraction, you can do some algebraic manipulations, and you know that you retained all the information you had, and you can somehow extract that information with algebra. So that's what we do. So right now, what you see in this demo, these edges that you see and these triangles are the parts of the simplicial complex. When two balls are touching, I'm endowing them with an edge. So all these points, they go into simplicial complex. That goes without saying. So they are already there. If they are, let's say, closer than some threshold, if I'm drawing these balls and I see that they are intersecting somewhere, I'm adding to that complex an edge. If I'm having 3 points and their balls are intersecting, like in here, so they all are intersecting, I'm drawing a triangle, and this triangle goes into my simplicial complex. But that's a geometrical simplicial complex, that would be. And I can abstract that, and I can work with an abstract simplicial complex and extract some information from there. What kind of information can I gain from there? So when I'm working with abstract simplicial complexes, so here is some sort of example. So we define so-called oriented n simplices. It's basically the simplex that we had, but I'm just endowing it with some sort of orientation. So I'm saying, okay, let this order of points, let's suppose it's positive. If I swap any two of them, I'm just like throwing away a minus sign. So I gain this minus sign. If I swap once again, I will get minus times minus is once again plus, and so on and so forth. That's okay. I define, it's really, I told you that it's a really heavy part, but what can we do? I should define a few more algebraic objects. One of them is the chain. So chains, they are some sort of formal sums of all of simplices of one and the same, I'll say, dimension with coefficients that in my case are taking from Z. So these are integers. They can be positive, they can be negative, but anyway, they are integers. There are different options if you get deep into the theory, but I guess most books are using integers, and I will do that as well. And now what can we do with these chains? Well, how do they look like? How do they look like? So here is, once again, example for you. So I had a triangle ABC, and I have created a simplicial complex that follows all the rules. So whenever I have something in here, I have its edges, its faces as well. So that's perfect. Now, let's look how chains look like. So 0 chains. I'm taking all the simplicial, all the simplices of order 0. These are points ABC, and I'm writing some sort of formal sum like this. So some coefficient x0, that is an integer, times a, plus x1 times b, plus x2 times c. So nothing special. So I have just combined them into this sort of construction. If I am talking about one chains, so I should take one simplices. These are segments. I have segment AB, I have segment AC, I have segment BC. I'm taking these segments and I'm just multiplying them by some integer numbers. So here is what I get. And if I get to the dimension of 2, there is only one simplex, just triangle ABC, and I'm multiplying that by some sort of integer number. So that's very easy. So here are the chains. What can I do with chains? I can do some algebra. I can add them, for example. So basically, these chains, they constitute some sort of abelian group. So I have an operation of addition. I have this minus sign when I'm swapping something, so on and so forth. So I can do that operations, and you can basically check yourself that all the whatever we need to make this a group, everything works fine. So that's what we have, but it's a bit not enough. Now comes the a bit, let's say, a heavy stuff. So we need something more. So just adding and playing around with chains will get us nothing. But here is one more operator. It's a linear map. It's called a boundary map, and it basically tells us how to calculate boundary of some simplex if we are, well, if we want to do that. So this is a central figure of the analysis that we perform. So why do we want that? Where are we going? We are going to calculating so-called BT numbers for the simplex and whatever is homology equivalent to that sort of simplex. So that's okay. So how do we do that? What are BT numbers? So BT numbers, in some sense, they calculate the number of, let's say, holes of different dimensions. It's a very hand-waving, let's say, statement, but it's basically the best what can we do without all that mathematical rigorousness. So we want to calculate somehow holes in there. And to do that, we need to fill, let's say, boundaries of the simplices we are working with. So here is an example for you. So let me draw that on a board once again. So suppose I have some simplicial complex that looks like this. I don't know, let's go with some A0, A1, A2, A3, A4, A5. And these are the triangles that are included. So this is a simplex, this one, and this one. And this is a hole in there, so nothing here. So just these triangles. And I want something that can fill this hole in here, some mathematical apparatus that does it. And how do I do that? I'm defining so-called boundary operator, and we will be playing around with that boundaries, and we'll be interested in two such things, all the elements, let's say all the possible boundaries, and all the elements that map to 0. So I guess I'll show you that in a minute, but what does the boundary operator do? So let's check with this triangle. So this triangle, it's what? It's some sort of A, B, C. And if I'm mapping that with the boundary operator, sometimes people set index 2 here to underline that it's boundary operator in two-dimensional space. And what I get at the end of the day, it's something like this. I'm trying to remove each of these vertices. I'm removing them, and whatever is left, I write down as the new simplex. And I'm placing signs plus and minus, like swapping them at each place, plus, minus, and so on. So let me show you that as an example. So I'll be removing, so the first one is A. I'll try to remove A right now. It's the first one, so it gets with the sign, let's say plus. So what it means, I get plus, B, C. The next one will be this B. So it's the next one, so it gets with the sign minus. So what I get is minus A, C. The next one is C. Once again, I swap the sign, I get plus, so it's plus AB. Now you can see that whatever I get in here, these all are simplices from my simplicial complex. So it wasn't in vain that I was demanding that whenever I have something, its faces should be in here. They should be in here for a reason. So when I do this sort of thing, when I'm calculating that border, I'm getting something from the simplicial complex. And you might guess, if I have, let's say, one chains, so I'm taking all the possible one chains, how do they look like? They look something like this. So you have some coefficient, I don't know, let's call it x0 times BC plus x1 times AC plus x2 times AB. You see that this thing is a particular case of this thing. So among all the chains that we have in 1D, this is some sort of particular case. Okay, we are closing in. Now a few more definitions. Yeah, I know it looks very complicated, but that's what we have. So-called D and B. Do I have it somewhere in here nicely written or not? No, I do not. Okay. So we are now interested in kernel of the boundary operator delta k and image of the delta k plus 1. And we want to find some sort of factor group with respect to these things. It may look a little bit strange for you, but let me put it this way. So image of this dk plus 1, it's the image from the previous layer. So when I had some triangles, this is the image, it's their borders. So whatever you get in this image, it's the borders, let's say hand-wavingly, of the triangles that are filled in. So they are all filled in. So there are no holes in that triangles. So that's what I have. Taking something factor, so factoring something out, like factor group or some and so on, you are some sort of neglecting something. So you are gluing them together or making them equal to 0. So it means basically this operation will mean I want to disregard everything that is filled in that has no holes in it. So that's what I want. Now, what is this sort of thing about kernel? This kernel is interesting as you know that the border of some border is always 0. So it means that I am considering some closed loops or some closed chains in there. So here it is. So that's why it's kernel. So kernel, it's everything that is closed. And now I'm disregarding everything that is filled in. And with that being said, I will get some construction that some sort of fills that holes that we have in the manifold. And doing the thing, I'm getting some sort of group. It's called a homology group. H from the manifold. And the interesting part is that this group can be decomposed. We have a theorem in algebra. Once again, it's a bit complicated. I can't prove it in here. That you can decompose that. You remember that I worked with integers into some part that is let's say, equivalent to the abelian group of addition on integers and some different parts of cyclic groups. The different part of cyclic group is called sometimes called a torsion. It can gain you some additional information about that. But what you are interested in is this rank, because this rank tells you how many holes of certain dimension do you have in that manifold. So, okay, looks complicated, looks hard. But let's take a look at some sort of more practical part. So here is an example I showed you. Let's try to run some good library in here and look at this thing. So here what you see is the radius that we have. So that's radius r that I'm changing. The yellow line shows you the exactly radius r that I'm using at the moment. These blue and green things, they show us basically some topological features. So what are these features? So these blue lines, they show us the existence of zero-dimensional topological features, or it's you can call it BT number of order 0, or it's the number of zero-order holes. Basically, that's the number of connected components that you have in here. So let's try just intuitively. Here I have separate points. Radius is 0, and the number of connected components will be the number of basically these points. If I increase this radius, some of the balls will be touching, and I will get the number of these components. It will become, let's say, 1 less. If I make radius even bigger and bigger, they are touching and touching, and you see that at the end of the day, I will get just 1 connected component. That's what I have. And this is basically detected with that sort of simplicial complex. So there is a really nice theorem, so-called NERV theorem, that tells us that the topology of this thing that I'm showing to you, this manifold, is the same as the topology of the Czech simplicial complex that we are building. And with that complex, the Goodhill library extracts me this nice picture and shows me what will happen if I change this radius and I get different results. The green thing in here will show me a number of these sort of holes. So you see right now a hole in the manifold. So I can draw some sort of curve, some closed curve, and if I try to shrink it to the point, I will be not able to do that in here because I have a hole in here where it's no manifold. And you see that when this radius is small, balls are not touching, and they are just like some separate things living separately. When I increase it enough, this circle is formed, and you see 1 hole in here. So a new topological feature has been born. So here it is. It will live for some time. So if I change radius, change, everything is okay. But at some point, this hole closes, and there is no more hole. And this topological feature just disappears. So that's what we have. So this is the intuitive idea. And what we'll be working with, we'll be working with these sort of diagrams in different cases. It's called persistence barcode. So here is an example for many points. I don't actually remember what did I use there as a manifold, so I used something. It can be represented in form of persistence diagram. You will see that a lot if you do some sort of topological data analysis. It's basically showing you the moment when topological feature appeared. So the left, let's say, side of this segment. Here is the burst, its x-axis. All the features of order 0, they are all born at the moment of 0. So you have no ball, but you already have all that components. And the axis y shows you when this topological feature dies. Of course, everything lives in the half plane upper. upper half plane because the feature cannot die before it is born. So that's quite obvious. Okay, what we do now? Let me show you now how these topological features work in some simple case when we have some simple topology and some noise. Oops, something failed. What failed? Okay, let me retry. Okay, not sure what happened. Doesn't really matter. So here are the blue dots. It's the points without noise. They have some simple topology. You can think of them as you get some, I don't know, some physical process, and this physical process, they makes them to live on this circle. It may be something very simple. I don't know, you have a pendulum, and this pendulum swings, and you are measuring positions of this pendulum, and just due to physical restrictions, all the points that you will get, they will live on one circle. That's perfect. But due to some error in measurements, you may get some points offset to these circles. So you may not like that, and you want to do something with that noise, and you want to extract some data from there without all that noise. So let's take a look at this picture and compare what we have in here. So here I am considering the homology groups of order 1. So I am basically trying to sense this hole in here inside. So I have a circle of points, there is one hole in there, and I'm trying to sense that hole. And you might guess from the intuitive point of view when you saw this picture, where is it? I've lost my demo. Here is it. So that if you are increasing the radius, at some point you have appearance of the topological feature, and at some different radius it will disappear. Okay, so what happens in here? So what do we have? So here is the clean data. We have some radius. We have one feature of order 1. Here it appeared, and at this radius it disappeared. So appeared at 0.25 or something like that, and disappeared at 1.75. Now here is the different data. Now it's without noise. And you see that it appears and disappears at, well, approximately the same numbers. So seeing these 2 points, you can compare them and say, well, they have some more or less reasonably similar topology. Okay, let's add some noise. Here I have added some noise. Here you see that some points have appeared on the diagram for the noisy homology group, but they are all near the diagonal. What it means? Something near the diagonal means that it was born and died almost instantly. So just appeared and disappeared. So it's clear, like say, it clearly shows you that there is some noise in the data, but you can remove that. And here is our stable topological feature that is once again quite close to the feature of the original data set. So it's quite noisy right now, but it's still, you can see with the topology that they are similar. I'm adding some more noise and even more noise. You see that this point is drifting away. We still see that there is one topological feature, so we still can guess how it looks like. And you see the data is quite noisy. So comparing these orange points to the blue points, you see that this data is looks quite messy. But we still can extract some information from here and understand what it is. The second thing, please look how this point goes away from the original point when I'm adding noise, and how it returns back when I'm removing noise. So distance between these 2 points can be some sort of measurement of the similarity between these 2 data sets that we have. In this exact case, it senses how much noise do we have in our data set. So you can extract some information on the noise that you have in there just by seeing these topological features. So you have more noise, they are getting far away. You have less noise, they are getting closer. So that's what we have. And it's a really nice thing to have because you can gain some intuition on the level of the noise in your data set, and you can compare your data sets and so on. And of course, we expect some similar behavior for comparing data sets. For example, when we are calculating all that cosmology, and we are putting like different parameters in there, some different physics in there, and we want, I don't know, to compare them. And of course, we would like to have something similar. So we will have some topological features, and they will be getting closer or further from each other, depending on how close were the physical parameters that we are putting in there. Okay, here is one more example for you. I know that I'm almost out of time, but it's almost end of the lecture, so just few nice examples for you. Maybe after the lecture you would like to, I don't know, to play around with that. So everything is in GitHub. It just starts in Google Colab. So my students know that I like these things. So here is a torus. So here we have it. Here are the points. So the red things, these red points, it's a data set I have generated. They all lie on the surface of the torus. And here is our persistence diagram that I have calculated from that with the Vitalii library. And here we see what? So homologies of order 1, you clearly see 2 points in here. And let me draw that for you in case you don't know what it is. So here is my torus. And here comes one topological feature. So it senses this thing. So it's empty inside. So it's basically a hole. And here comes the other one topological feature that senses this hole. So that's what we have. So that's why you have 2 points in there. So here, the green thing, it's a topological feature of order 2. So you may guess that the torus is encloses some volume inside. So here it is. And here is some sort of noise. Of course, it's noisy because you see how messy is the data set and how small is the number of points compared to the surface. So here are many other examples that you can use and, I don't know, check what's happening in there. For example, a sphere. So here it is. And once again, you might guess that you have no like one order features in here, but you have a feature of order 2. Here it is, this green dot, because it's enclosing some sort of volume inside. And if you take, I don't know, a Mobius strip, you will get something quite different in here. So you are like filling, this method is filling a hole in this strip. So here it is. But there is no volume enclosed, so you don't have any stable features topological of order 2 because no volume is enclosed. So that's what you have. Okay, now very quickly, we have these features, we have these sort of diagrams, and the last question is how do we compare them? And we compare them with the help of the Wasserstein distance. I just want to show you a nice example of that. So here is my points from diagram number 1. Here is my points from diagram number 2. And this demo shows you that we are basically trying to find pairs of the points that are as close to each other as possible. So you can think about it like taking all possible combinations and pairing the points as you can. If point does not have any pair, you are creating a virtual point on the diagonal. And this means that if you have this point on the diagonal, it's just appeared and disappeared. And this is the last demo that you have. It's the same demo that we had previously. I'm just quickly starting the code to show you. It basically shows you the same thing with that circles and topological points, but I have added a calculation of Wasserstein distance in here. It's of the infinite order, so it's called a bottleneck distance. And you see that these points are correctly paired. And you may observe how it changes when you are increasing or decreasing noise. So smaller noise, a smaller Wasserstein distance, bigger noise, and you get some bigger distance in here. So that's what we have. And basing on this, as you might guess, we have modeled some sort of topological all this. We have extracted all these topological features for different models in cosmology, and we tried, let's say, to guess whether they can fill some physical parameters in there. And here is my last image I'm showing to you. It's the comparison. Well, I don't know. It's frozen, but but the plots there, they show that this sort of thing is it can more or less sense the difference in the sigma 8 parameters. So here is the Wasserstein distance. Here are results that we had, and some sort of level of noise. Noise. Well, no, I guess. I'm sorry. No, it's not for our work. I guess it's from some example, maybe the previous one. Okay, but we have in our work very similar plots, but they show it's not noise in here, but sigma 8 that we were studying whether this method can sense this difference or not, and they look pretty similar to this ones and show that it can be sensed. So with that being said, I guess I'm complete. So yeah, it's 3 o'clock. Yes, I guess I'm in time.
Yes, just in time. Thank you very much for the lecture. This also mathematical theoretical overview of some background needed. I guess we should move to the questions now.
Yes. If we
So
have
yeah,
some questions.
yes, we do in fact. So just give me a second to make demonstration. Now everyone should see the slider menu, right? So again, I'm reading them aloud and you are answering. So the first one is, do you have any experience applying TDA to other areas than cosmology, from nature sciences or maybe something IT related?
Well, my experience comes mostly from cosmology, so we are working basically on that. But as far as I know, there are some IT-related things with the topological data analysis. For example, people tried to analyze some time series. So at the beginning of the lectures, I showed you there is people are trying, let's say, to convert time series into some sort of points in multidimensional space and tell that and suppose that they live on some sort of manifold and analyze that manifold. So there are definitely some works, but on my own, I didn't try something like that. So maybe in the future, we will find some more areas to test our methods.
Great, thank you very much. So we're moving to the next one. Is topological data analysis used in dimensionality reduction? Remember hearing something from a colleague.
Yes, it is used, but not the part I have showed you today. Today we were mostly focusing on the homologies and so on. But there is really a big branch of topological data analysis concerned with the dimensionality reduction. And you may heard it about under the name of manifold learning. So we have a number of methods of the manifold learning, like, I don't know, multidimensional scaling, isomap, locally linear embedding, and so on. And these are the methods of, let's say, they are shared between classical machine learning and topological data analysis. So yes, you are absolutely correct. Topological data analysis is used in dimensionality reduction, but it's a bit different methods. You may want to check on the GitHub. There are my lectures on the machine learning, on the classical machine learning, and the last, I guess, the lecture number 16, is devoted to manifold learning, and it's basically the methods of dimensionality reduction with the help of topology. It's more practical oriented, but yes, you may want to check that if you want to know more.
Great, thank you very much. And the last one, please suggest some literature to get started. Maybe you know good overview papers.
Oh, I guess I saw some interesting books about visualization and topological data analysis, but it's really hard to, I don't know, to remember them right now. Maybe we will, I don't know, we have some sort of chat or something like that. Maybe we'll post some references a bit later. So I will check what books do I have, what did I use to study all these things, because it's really hard to come from, let's say, from the top of my head. So maybe we'll be sharing, I don't know, some sort of links, for example, for my presentation and maybe for the lectures that we have in case someone wants to check for the dimensionality reduction, and I'll add the books.
That will be wonderful. Yes, we do have a Telegram chat, and most of the people who register to the school have already joined the chat, and it is basically for reminding about lectures and for sharing the materials from the lecturers. So it would be really nice of you to make such a collection of links, like the link to the GitHub with today's lecture notes, the link on the GitHub with that lecture from machine learning course we just talked about, maybe also some names of the books or papers that you will just find today, or and then just we will post it as, or maybe you can also yourself join the chat and then just write there.
Okay, yes, I'll do that. I'll do that. Okay, I'm writing down what I need to share, and I'll do that, I guess, even today in the evening.
That will be very nice. Thank you.